Hello again. Now our first example was about Otto cycle, and Otto cycle are the cycle to simulate the operation of our gasoline engined internal combustion engines. Now the diesel cycle example, where we call it as air standard diesel cycle, it is similar, but it demonstrates or simulates the diesel engine better. From 1 to 2, we have as regular, as in the dual cycle case, isentropic compression. Now 2 to 3 is constant pressure heat addition to the air from an external source. Now we had it also in the Otto cycle. If you remember, we have also 1 to 2 compression, but 2 to 3 we had heat addition at constant volume. However, in a diesel cycle, or where we call as the diesel cycle, we have 1 to 2 again similar, but this time instead of going up we go at constant volume, at constant pressure. Okay, so here we have heat addition at constant volume, we have at constant pressure. This is the major difference. The remaining is same as you go here and as you go here. Okay, so this is 1, 2, 3, and 4. So the major difference now, we have work during heat addition from 2 to 3 and 3 to 4. However, we don't have any work term for Otto cycle. This is the diesel cycle. Okay, so these are the major difference between them. Now, the pressure and temperature, if you look at the example, the pressure and temperature at the beginning of compression of an air standard diesel cycle are 95 kilopascal and 300 Kelvin. At the end of the heat addition, the pressure is 7.2 megapascal and temperature is 2150. What's the compression ratio? What is the cutoff ratio, which is specific to the diesel cycles? The thermal efficiency of the cycle and mean effective pressure. So this was the similar requirements for the Otto cycle example. So if we look at the solution, we have a PV diagram where we go from 1 to 2, 2 to 3, and 3 to 4, and we have 1. So T1 is 300 Kelvin, P1 is 95 kilopascal, and we have 95 kilopascal, and T3, in terms of T3 we have 2150 Kelvin. Okay, and we have also similar case, this time air also. Now again we are gonna start by fixing each state. Okay, and we are gonna fix each state by using table A22. Okay, so for the state 1 we have T1 is equal to 300 Kelvin, P1 is equal to 95 kilopascal, Therefore U1 is read from the table, kilojoule per kilogram, and we can look at the VR1 as 621.2, PR1 as 1.3860. Okay, so for the state 2 we have isentropic compression, where PR2 is equal to PR1 P2 over P1. Okay, so that's gonna be equal to 1.3860. These are the pressure ratio, which is 105.04. So from here we go to table A22 and we read T2 as 979.6 and VR2 as 26.793, and this we will need H2 as 1000 enthalpy 22.82 kilojoule per kilogram. So for state 3, what we know, this is the state 3, okay, we know P2 is equal to P3. T3 is also known to 2000 Kelvin. P3 is kilopascal. Therefore, we can go and read from the table and 2440.3 kilojoule per kilogram, and VR3 is 2.175. So if you go to state 4, what do we know about state 4? State 4 is here, and for the isentropic expansion, we can write this V4 over V3 is equal to V1 over V2, V2 over V3. Okay, so this ratio is known, and what we can write here, V1 over V2 multiplied by T2 over T3, or we can write it VR1 over VR2 T2 over T3. So from here we can calculate this as V4 over V3 as 621.2 to 26,793 979.6 2150, which is going to be 10.56. Therefore VR4 is equal to V4 over V3 multiplied by VR3, which is 22.98. Therefore from the table we can easily read and U4 as 785.75 kilojoule per kilogram. So the requirements, what is required? The compression ratio R is equal to V1 over V2. Also that's going to be equal to VR1 over VR2 from the table. 26.793, which is 23.19. As you see, the diesel engines have much higher compression ratios. Cutoff ratio is defined as RC V3 over V2. This is cutoff ratio. Cutoff ratio. And you see here V3 over V2, this ratio. And this is specific only diesel engines, specific to diesel engines. And RC is also equal to T3 over T2, which is going to be equal to 0.6, 2.19. This is the cutoff ratio. The thermal efficiency of the cycle is, as you know, we cycle over m divided by Q23 divided by m. So that's going to be equal to, we cycle H3 minus H2. Now we have two terms, H3 minus H2. So we have some work here, okay, from 2 to 3 and 3 to 4. So expansion starts from 2, expansion work is all the way to 4. So H3 minus H2, okay, so this is a minus, okay, so this is H3 minus H2, U4 minus U1, U4 minus U1, okay, so here U4 minus U1, H3 minus H2 minus U4 minus U1, okay, so this is the cycle work divided by Q23, Q23 is H3 minus H2, divided by H3 minus H2, so that's gonna be equal to 2443 minus 82 minus 5 minus 21407 divided by 244.3 minus 82. So this efficiency is going to be larger than the efficiency of the Otto cycle, which is 0.597. This is typical to diesel engines where they have higher efficiency.